What's up, space nerds? Let's talk about one of the most fundamental equations in rocket science. So, why should you listen to me? Look at all these model rockets behind me. The Kerbal Space Program music and the shape of my hands symbolizes that this dude knows what he's talking about. Anyway, let's get started, shall we? To get started, let's have an imagination of what happens inside the combustion chamber just after combustion has taken place. So inside the combustion chamber, you will have these hot gas particles that have just been released as an effect of combustion, okay? And the energy they contain is in the form of temperature and pressure. These gases with this energy begins to expand against the walls of the nozzle and the combustion chamber. By expanding, these gases exert a certain force on the walls of the combustion chamber and the nozzle. And we know from Newton's third law of motion that every action has a reaction. This action of expansion prompts a reaction from the walls of the combustion chamber and the nozzle. And it is this reaction that forces the gases outside through the nozzle. Since pressure is given by force divided by area, we can say that this force that accelerates the gases outside, or the reaction of the walls of the combustion chamber and the nozzle, is given by the pressure of the combustion chamber and the nozzle times the area. Okay, at this point, we can see that we are already representing the thrust or the force acting on the gases in a more informative way. We're already seeing that the force that's acting on the gases is totally dependent on the pressure that we can actually achieve inside the combustion chamber. And this is a really more informative way. It tells us that to get more thrust or to get more forces on the gases, we have to increase the pressure that we will achieve inside the combustion chamber. But everything does not happen in a vacuum, and we have to consider the effect of atmospheric pressure and outside pressure. For the cases of the gases, let's consider a very small area at the exit, which we'll say area E, which is the area of the exit, and we'll have a retarding force given by the pressure at the exit times the area at the exit. This is a huge complex topic that cannot be explained in this video, but to get you started, maybe you might look at what happens when flowing gases interact with other fluids. This will give you an understanding. But to summarize it, we'll say that there is a retarding force at the exit given by pressure at the exit times the area at the exit. We will then subtract this to get that the final force that accelerates the gases outside the nozzle is given by this, which is the pressure times area of the combustion chamber and the nozzle minus the retarding force that is given by pressure at the exit times the area at the exit. We've really come a long way to get to this beautiful equation, but no journey ends without consulting with the Newton. So, what does Newton have to tell us about the forces that act on the gases? In his second law, Newton tells us that force is given by the rate of change of momentum. And if we simplify this for the rocket, we can basically include that the force or the thrust of a rocket can be given by mass flow rate times the velocity of the propellant at the exhaust. But he doesn't stop there, does he? He gives us a third law that tells us that every action has a reaction. And the forces acting on a gas given by this can now be equated to the thrust that we have for the rocket. Therefore, we can end up with this final equation. Okay, we've contacted the greatest sage, Newton, and he has given us something to live by. But looking at this equation, there's this squiggly bracket which is basically very daunting. So, how can we get rid of that? To simplify this equation, let's consider the forces that are acting on a rocket. We've already spoken about one of them, that is the pressure inside the combustion chamber that actually acts against the walls of the nozzle. And just as the same reason, the rocket itself does not operate in a vacuum. There's actually a retarding force that's caused by atmospheric pressure. We can then substitute this to get that the force acting on a rocket will be given by just the pressure times area minus the atmospheric pressure times the area of the exit. So equating these three equations, just as Newton told us, we can then simplify to get the final equation that the thrust of a rocket will be given by mass flow rate times the velocity at the exhaust plus pressure at the exit minus atmospheric pressure times the area at the exit. So what's the point of going through all these steps? Well, I want you to think about what we noticed when we were deriving this equation. We saw that thrust is given from inside the combustion chamber and the nozzle. So meaning, when we're designing our rocket, the materials holding the engine from the combustion chamber must be strong enough to handle the forces of thrust that they receive. And the subsequent material, which is especially the tanks themselves, should also be strong enough not only to handle the pressure of the fluid in them, but also to be able to handle the forces of thrust that they receive and transfer these forces throughout all the rocket parts. But you might have noticed that something else is missing: effective exhaust velocity. I mean, what's the point of having this long equation when we can say that the thrust of a rocket is just given by mass flow rate times effective exhaust velocity? So, what is that? Now we have this equation to tell us what the thrust of a rocket is, but there is another equation that tells us that force is given by mass flow rate times effective exhaust velocity. So what is this effective exhaust velocity? If we substitute it to our equation, we get that effective exhaust velocity is actually just given by the real velocity plus the effect of the atmospheric pressure. So in a way, this equation just simplifies the other equation by not making it such a very wordy equation. So the two are equal, but it is also important to know what effective exhaust velocity really stands for. And we've reached the end of our video. That was it for today. If you have any other question, consider reaching me out on my social media handle and I'll be really happy to help. Thank you.